Alright guys, welcome to today's lesson in statics. Today we're covering problem 121 from chapter 2. So problem 121 says, a container of weight W is suspended from ring A. Cable BAC passes through the ring and is attached to the fixed supports at B and C. Two forces, P equals Pi hat and vector Q equals K hat, are applied to the ring to maintain the container in the position shown. Knowing that the weight is equal to 376 newtons, determine P and Q. Hence, the tension is the same in both portions of cable BAC. That's correct. As we can see, there is a frictionless ring here. Whenever a cable passes through a frictionless ring, we do have the same tension in both components of that cable. Okay, so let's go ahead and get started. First thing we're going to do is, of course, draw the free body diagram. So we're going to draw this at point A. Okay, we have, of course, the weight pulling that point and that hoop, that ring straight down. This weight is equal to 376 newtons. We have force P acting along the x direction, the x-axis direction. That's vector P. Its only component is on the x-axis. And vector Q's only component is along the z-axis. So we'll draw those in, label them as well. And of course we have the tension in the two rings, tension in two cables supported by the ring, as being tension BAC for both. Okay, so get a good view of that for you. Alright, so we're going to need to find the components for both vectors here and here, and then calculate what vector Q and P are based on what these components supporting this weight happen to be. So first thing we're going to do is calculate the position vector for the point A to point B. Okay, and notice we have our dimension in millimeters. We're going to keep those millimeters for now. It will, however, be in future chapters be important to convert those into your base units meters. So looking at, let's say, A to B, we're going, let's say, it looks like 130 millimeters in the negative x direction. So leave it as negative 130. And for this video, I'm going to leave off units just to make things simpler. But it will be important to include units in future videos. Okay, so we have negative 130 in the I direction. We have a distance going up positive 400 millimeters in the j-head direction. And then it looks like we're going 160 millimeters in the positive z-axis or the positive k-hat direction. Okay, I'm going to go ahead and also calculate what the vector is for position vector is for A to C. We'll do both of these in parallel at the same time. So A to C is slightly different. We're going 150 millimeters in the negative x direction, or negative I hat direction. We're going again up 400 millimeters in the j hat direction. And in the z-axis, we're going the negative z-axis, negative k hat of 240 millimeters, so minus 240 millimeters in the k hat direction. Now I'm going to go ahead and calculate what the distance is for each one of these position vectors by doing the magnitude calculation. So distance AB, we're going to calculate that. We know that's going to be the square root of these components squared and added together. So it would be negative 130 squared plus 400 squared plus 160 millimeters squared. So that distance we know now, we can calculate it. Alright, so we have in the calculator negative 130 in parentheses squared plus 400 squared plus 160 squared. We take the square root of this number, and our distance works out, oops, 1 second, I did a minus sign. So let's start over. Let's type this out all in one line. How about that? So let's start off with saying negative 130 parentheses squared plus 400 squared. Again, we don't need to put parentheses around values that don't have negative signs. And then plus 160 squared. Okay, the square root of that answer, we get 450 millimeters, which is a good answer. Okay, we'll do the same thing and go ahead and calculate our distance value for position vector AC. So we take the square root of its components, add it together, square and add it together. So we have negative 150 in parentheses squared plus 400 squared plus negative 240. Again, we'll write these in parentheses. We won't need to include parentheses in the calculator around ones that have negative signs. Negative 240 squared. Okay, so we have in parentheses negative 150 squared plus 400 squared plus, in parentheses, negative 240 squared. We take the square root of this number, and that gives us a distance value of 490 millimeters. Okay. Next, moving on, we're going to write the vector component form for tension AB and tension AC. So, we write this out here. We have tension AB. Remember our formula, it is simply the scalar value divided by the distance AB, tension AB divided by distance AB, and then multiplied by the position vector RAB. So if we were to write this out, it would be tension AB divided by the distance, which we know is 450. This is units of millimeters, but we know we have units of millimeters here. They'll cancel out. We're going to divide each one of these. So let's write it out first. So we'll write this as negative 130 I hat plus 400 J hat plus 160 K hat. So we're going to divide each one of these components of our position vector for A to B, from A to B, by the distance A to B, 450 value, millimeters, and we'll get our coefficients for our vector tension AB. Okay, so we have negative 130 divided by 450. All right, we have a value of negative 0.289 times tension AB. We'll put these coefficients in parentheses. All right, this is in the I hat direction. I'm going to write these vertical to save space. We have 400 divided by 450, which is going to be positive 0.88. We'll round this up to 9, tension AB, in the J hat direction. And then finally, we'll divide our 160 for the K hat direction by the distance value of 450. So 160 divided by 450. Okay, and that gives us a component with a coefficient of 0.35 repeating, so we'll round this up to 6. Okay, and then this tension AB again in the K hat direction. So we have our components for tension AB, all right, and this is also going to be actually, I apologize, this should actually be tension BAC, because it's the same, it's the same in both components. So there's actually tension BAC for our tension value. It'll be the same in both cables, so tension BAC, not tension AB. These have the same tension values. Okay. So tension BAC instead. Okay. Now we're going to do the same thing, but for our tension value, or tension vector, I should say. The vectors have different position components. from A to C. And this will equal to now tension BAC over distance AC times the position vector R A to C. Okay, so we have our tension BAC unknown. Our distance from A to C, though, we do know is 490 millimeters. We're going to multiply that, essentially divide it by our components in our position vector of negative 150 I hat plus 400 J hat minus 240 K hat. So we're going to divide each one of these. So we have negative 150 divided by 490. We get a coefficient of negative 0.306. And tension, multiply by tension BAC. All right, we have 400 divided by our distance of 490, 0.816, so plus 0.816 in parentheses, tension BAC. And then we have this again, this is I hat. Don't forget our component, our unit vector components, J hat, and then plus negative 240 divided by 490. So negative, in parentheses, negative 0.490 rounded up. Tension BAC in the K hat direction. Okay, so let's focus this. Okay, so now we have our two tension vectors. They have unknown scalar magnitudes, but we do have the components broken down into the I hat, J hat, and K hat directions. All right, going back to the figure now, I notice value of P is unknown, value of Q is unknown, but the weight of this bucket is known, which essentially means, since I know that, which essentially means I can solve for the Y component, I can solve for the Y direction, and I know this weight, I know this force, and these are broken into their Y components. I can sum force in the Y direction, in the Y axis, and that will let me solve for the tension in BAC. Okay, so we're going to say, I'll show this in the frame real quick. We're going to say summation of forces in static equilibrium. Summation of force in the Y direction is equal to 0. All right, so let's sum force in the Y direction. In the Y direction, I have my tension BAC from A to B and tension BAC J hat for A to B and A to C. So we'd have positive 0.889 times tension BAC, and then we have plus another 0.816 times tension BAC again, in J direction. And then don't forget I have my weight. We have this weight pulling down. So this weight is pulling down. They tell us with a force of 376 newtons, so it's pulling down in the negative Y hat, negative J hat direction, so it's minus 376 newtons, equal to 0. Now I can do a little algebra here. I can group these two terms together. So I'd have tension BAC, and then I would have this coefficient 0.889, and this coefficient 0.816. I factor the tension BAC out of both. I can move this value over here to the right-hand side of the equation, make it positive, equals 376 newtons. We can divide by this value, and we go ahead and calculate what this value is. So let's see, it is 0.889 plus 0.816, which is 1.705, so I can divide by the same thing. This is 1.705. This cancels out. This is the same thing. And I divide by 1.705. And now this tells me that my tension in cable BAC is going to be equal to this number. So it's going to be 376 divided by this answer we just got. It's 220.5 newtons. That's the tension in cable BAC. The question doesn't ask us for that. We do need to find them in order to determine P and Q. Now, by some forces in the x direction, knowing what tension BAC is, I can now calculate vector P, which is also strictly in the x direction. So the summation of forces in the x direction equals 0. Okay? So let's see. This would tell us, first of all, I have vector P acting in the x direction. So I'm going to write vector P, scalar magnitude right here. And then we have tension BAC from A to B and A to C as well. So let's look at what the I hat components of those are. All right, tension in A to B. All right, the I hat component is negative 0.289. So this would be minus 0.289 times the tension we know now. The tension is 220.5. Okay. I'm going to add in the next component. All right, tension A to C. Well, this has a component. Let's see. It looks like tension A to C has a component of, we're in the x direction. That's right. Negative 0.306. Yes, negative 0.306. So we're going to write negative 0.306 times the tension BAC. It's the same in both cables is attached to the ring. It's the same for both. 220.5 newtons. Okay. So we're just going to multiply these together first. Then we'll combine like terms. Let's see, this will be equal to 0. So going back to the calculator, negative 0.289 times 220.5. All right, and then plus in parentheses negative 0.306 times 220.5. So we get a value of negative 131.2. So this is P minus 131.2 newtons. That means P is going to be equal to, if we move this to the right-hand side, vector P is equal to 131.2 newtons, and it's acting on the x-axis only in the I hat direction. So here's a value of vector P. Okay, now we can do the same process and solve for vector Q. So summation of forces in the z direction equal to 0. Okay, so we have the Q vector, the component of Q, it's only acting in the z direction, so we have the Q vector in the z direction. Okay, so we have Q, and look at the K components. K component here would be positive 0.356. Tension BAC we know is 220.5 newtons. And then plus, we're going to take the coefficient for AC, which we have negative 0.490 times 220.5 newtons. Okay, so equal to 0. We'll multiply this out first. So Q plus, let's see, it might not be plus. Let's find out. Go to the calculator, so 0.356. Oops, let's see. 0.356 times 220.5 plus, in parentheses, negative 0.49 times 220.5. We get value of negative. It is negative. So let's get rid of this plus sign, make it simple. We're subtracting, so it's minus 29.6 newtons equal to 0. And that will mean Q vector in the K direction, in the Z-axis, acting on the Z-axis, equal to positive 29.6 newtons in the K hat direction. So that is our answer for vector P. We get 131.2 newtons I hat, and vector Q, 29.6 newtons K hat. Thank you and have a good day.
Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.